Hello and welcome to our State of the Science snapshots from the Science and Technology team at the Good Food Institute. I'm Liz Specht, Senior VP of Science and Technology, and I'll be joined today by several of my colleagues to highlight the most exciting developments happening in the science and technology ecosystem for alternative proteins. These snapshots are presented 3 times a year, and each snapshot covers noteworthy developments over the prior 4-month period. Of course, this field is moving far too quickly for us to cover all of the advances in a comprehensive way in a short video like this. So these snapshots are intended to serve as a highlight reel curated by our subject matter experts and team leaders. For this State of the Science update, we'll be mostly focused on scientific advances that have happened recently and some newly published environmental analyses. But I did want to just first highlight one incredibly exciting update on the talent and training ecosystem. I'm delighted to announce that this summer we officially welcomed 24 new groups to GFI's Alt Protein Project, which is our network of student chapters at leading academic institutions across the globe. This new cohort brings our total number of chapters to 53, including establishing a footprint in 6 new countries, including Switzerland, Turkey, Portugal, Brazil, Malaysia, and Japan. We were thrilled to have student representatives from many of these chapters, and these new chapters, as well as our existing chapters, join us in person last month at the Good Food Conference. There, they spent a whole day dedicated to strategy and planning and serving as catalysts for alt protein research and talent development on their campuses. And they're now taking this work back to their institutions this fall. So please do stay tuned for our next update at the top of 2024 to hear more about what they've been able to accomplish in the last few months of the year here. Now I'm excited to turn it over to our technical subject matter experts. We've got Nikita Kogar, Lucas Eastham, Elliot Swartz, and Claire Baumkamp, who will talk about what has caught their eye over the last few months in terms of new research successes and noteworthy publications in each of their zones of expertise. Finally, Simone Costa will provide updates on ecosystem-level analyses that are helping to guide R&D and commercial activity across the sector, again, with a focus on some environmental analyses for this State of the Science update. I'd also like to give a shout out to my colleague Renee Bell, who helps to organize and manage all of this information to make these snapshots possible. One overarching comment I'd like to make about the technical advances we'll cover this round is that several of these are actually from original analyses commissioned or conducted by GFI, and our speakers will highlight those where they come up as we go through. For each of those analyses, we have full webinars you can watch that delve into much more detail, so I definitely encourage you to check those out. And with that, I will hand over to Nikki.
Thank you, Liz. Today I'll highlight some of the many technical developments for plant-based proteins from the past 4 months. GFI recently launched an analysis on plant-based meat manufacturing capacity and pathways for expansion in collaboration with Bright Green Partners. The 4 main takeaways from this analysis are as follows. Globally, we estimate total capacity for plant-based meat post-processing and extrusion, and find that even moderate growth may outstrip the industry's ability to serve demand. We also demonstrate that retrofitting facilities can be an agile and affordable solution for capacity growth, where retrofitting on average requires 1/5 of the capital expenditure and 1/3 of the lead time compared to greenfield. Greenfield construction can be the best choice for manufacturers that have enough capital, are okay with longer lead times, and want to focus on long-term efficiency. Manufacturers engaged in greenfield construction should implement sustainable technologies and automation to lower production footprint and costs. Finally, our report highlights opportunities for incumbent industries to apply part of their infrastructure to production of plant-based meats. Check out the full report and webinar on our website for more details. A major trend that emerged this cycle was the use of biological and heat processing techniques to improve plant protein extractability, digestibility, amino acid profile, flavor, and allergenicity. Here we highlight 2 notable examples where such treatments were used to improve the flavor profile of plant proteins. In the first example on the left, researchers at Nanjing University and the University of Manitoba enhanced the flavor profile of rapeseed protein isolate through enzyme and ethanol treatment. They identified hundreds of volatile compounds in the protein isolate and showed that this treatment significantly altered these compounds, which reduced sourness and enhanced sweetness and fruitiness. These techniques can also be combined for multiplied benefits. In a notable example on the right, researchers at the VTT Technical Research Center of Finland combined lactic acid fermentation with high moisture extrusion processing of pea protein to form plant-based sausages. The sausages were prepared by extruding a mixture of fermented and unfermented pea proteins. The researchers showed that the fermented sausages have improved texture and flavor, particularly through the bacterial expression of glutamic acid, which is connected to umami flavor. There are many methods to isolate protein from crops, each of which has unique impact on the protein functionality and performance. Here we will highlight two notable examples related to the fractionation of mung beans, a popular legume used in plant-based meat, egg, and other applications due to its high solubility and protein content, along with advantageous gelling behavior and savory flavor. In a paper recently published by GFI grantee Meek Schlangen and colleagues, mung bean protein fractions were obtained through 4 distinct methods. The report focuses on enzymatic transglutaminase cross-linking of these fractions, which is commonly used to improve gel strength and water holding capacity. As shown in the figures on the right, each fraction responded differently to transglutaminase. To explain these findings, the researchers showed that fractionation method controls susceptibility to transglutaminase because it partially controls protein conformation and solubility. Relatedly, Eat Just, a California-based developer of alternative egg products, patented their mung bean protein fractionation procedures for enhanced functionality. Their fractionation procedures include dry and wet methods, and sometimes include transglutaminase treatment, advanced filtration techniques, and other methods. These methods are geared towards recreating the functional properties of animal egg proteins that are advantageous for a variety of food applications. Plant-based fats that can mimic the desirable properties of animal-based fats with improved nutritional value are a perennial target. Here we highlight 2 impressive results that use little to no fat ingredients to emulate the characteristics of conventional animal fats. First, on the left, researchers at the University of Leeds developed plant protein microgels to combat their astringent or drying off sensation. With the key ingredients of just plant protein and water, the researchers created a protein microgel that effectively traps water around the plant proteins and even replicates the performance of an oil and water emulsion. As the production involves commonly used processes and relies solely on protein and water, these microgels provide a much-needed platform to address juicy mouthfeel for plant-based applications. On the right side, researchers at Iowa State University combined hydrogels and oleogels to create biphasic gels, also known as bigels, that are capable of replacing commercial fats like butter and shortening in short dough applications. In fact, the bigel shortbread cookies were more tender but presented similar microstructure and moisture content compared to traditional shortbread. Furthermore, the bigels do not require the use of emulsifiers and showed marked improvement over vegetable oil spreads, representing a suitable plant-based alternative to commercial solid fats. Finally, we will touch on 2 reviews that take a soft matter physics approach to elucidating the many phenomena associated with the development and production of plant-based foods in an effort to boost the design and development of next-generation plant-based meat, seafood, egg, and dairy products. First, on the left, researchers at Wageningen University reviewed the physicochemical processes that occur during high moisture extrusion. They subdivide high moisture extrusion into several tasks according to particular sections of the extruder. They pose that structuring happens at 3 different length scales, from nanometer to millimeter scale, as the processing time increases. They gathered these and many other hypotheses concerning each part of the process, not only from food science literature and patents, but also from other areas of science where similar phenomena exist. Although many of these hypotheses require further investigation, this review gathers information from diverse areas of knowledge to inspire the field. To that end, the researchers provided an appendix with suggestions for further experimental analysis. Next, GFI grantee David Julian McClements reviewed the soft matter physics principles associated with modeling the mechanical properties of plant-based foods as measured by rheology. Since many of these products are comprised of colloidal materials containing particles or polymers, their properties are readily understood using soft matter physics, material science, polymer science, and other related disciplines. In this review, Dr. McClements describes theoretical models to identify, predict, and control the key parameters that impact the textural attributes of plant-based foods, including low and high viscosity fluids like milk and cream, soft solids like yogurt, and hard solids like some cheeses. And with that, I'll hand it off to Lucas for some exciting fermentation-focused updates.
Thanks so much, Nikki, for those great updates. Today, I'll cover several great developments across the alternative protein fermentation sector. So first, in July, GFI and Integration Consultant published our analysis on fermentation manufacturing capacity and pathways for scaling. The full white paper and the webinar recording are now available online in the QR code that you see below. The main findings from this analysis included that there are at least 16 million liters of food-grade production capacity worldwide, with the highest concentrations in Europe and North America. And within this production volume, there appears to be a need for more multi-purpose pilot and demonstration scale fermentation facilities. The analysis also assessed the major metrics that influence the choice between either building your own facility or going to a contract manufacturing facility. And then finally, the analysis also assessed retrofit opportunities and found that biomass fermentation is more aligned with retrofit feasibility. Check out the report for all the details. Next, I wanted to highlight fermentation technoeconomic analyses, which really help determine the scalability and identify opportunities to reduce costs for commercial production. In the past few months, we've seen several TEA publications, along with the new Scalar TEA tool put out by Synonym Bio. First, researchers at UC Davis published an open access TEA for mycoprotein production that is based on the corn process. Their TEA found that mycoprotein production is very sensitive to nutrient source cost inputs, but can be produced for less than beef. What we really like about this paper, though, is the open access editable spreadsheet that they provided in the supplementary material, and it has all their assumptions, calculations, and price estimates. Many TEAs utilize process simulation software that requires an initial economic investment and require additional training. So having an open source Excel model really overcomes this challenge and allows the user to have control over their inputs and quickly assess the TEA. In the second paper, researchers at Ghent University and Biobase Europe Pilot Plant developed a comprehensive TEA model that assesses a carbon-neutral two-step fermentation process, where first, industrial furnace off-gases are converted to acetate by Morella Thermoacetica, and the acetate produced in that fermentation is then used as the feedstock for the biomass growth of the strain Cupervatus necator. This strain has really high protein content, a nutritious amino acid profile, and better digestibility than other common protein sources. The analysis points to economies of scale for unit production costs, but diseconomies of scale if production capacity is increased too far due to excessive capital investment beyond significant cost reduction. Now, the diversity of the microbial world is all around us, and it can help produce proteins and lipids in stunningly sustainable ways and help bring delicious, nutritious food to our plates. So it's always great to see prospecting and characterization of microbes for fermentation-derived food ingredients. And a major trend that we've noticed across research papers and patent applications is the use of bacterial strains for development of alt protein and more. Specifically, researchers at Shenzhen University and Shenzhen Institute of Industrial Biotechnology put out several publications for strain development in bacterial strains like Corneobacter glutamicum, Bacillus subtilis, and Escherichia coli for the production of food ingredients such as leg hemoglobin, lycopene, and the amino acid L-leucine. And in one recent study, they showed that Corneobacter glutamicum, a gram-positive bacterium, can produce high titers of globin proteins of up to 20% of its total cell biomass. And they demonstrated production of leg H, or leg hemoglobin. Cornybacterium has been increasingly recognized as an attractive host for production of alt proteins due to its readily available genetic engineering tools, its rapid growth in minimal media, its generally recognized as safe status, as well as its established industrial scale use for amino acid production. Elsewhere, researchers at Chalmers University of Technology in Sweden extensively characterized a novel oleaginous yeast strain called Pseudozyma hubaensis, which is capable of really high lipid production while consuming both glucose and xylose simultaneously. This is not very common in most commercial strains and can help enable the valorization of cellulosic feedstocks. The researchers also produced the first transcriptome study of Pseudozyma hubaensis and made all of their genome and transcriptome data publicly available in databases. I want to talk about fermentation-derived ingredients and how they have the power to improve the taste, texture, and nutritional characteristics of our food. And studies that assess this end product functionality and digestibility are extremely important for taste and nutrition parity. However, these are not as prevalent in our field yet, so it is always great to see a few recent papers address this gap. First, on the left, researchers at the University of Borås and Chalmers University in Sweden, they assessed the in vitro, meaning outside of the body, protein digestibility of 5 edible filamentous fungi. And they compared this to beef, chicken, salmon, and casein. They assessed the commonly used commercial strains like Aspergillus oryzae, which is used in koji, Neurospora intermedia, used by Better Meat, Fusarium venenatum, used by corn and enough, as well as Rhizopus oryzae and Rhizopus oligosporus, commonly used in tempeh. The paper provides an excellent overview of the static InfoGest in vitro gastrointestinal digestion protocol, as well as the reduced enzyme modification they made to improve the method. Their evaluation found that the protein degree of hydrolysis and the amino acid accessibility of the 5 fungal species were highly comparable to chicken, salmon, and beef, which indicates that these edible fungi are a nutritionally sound protein source. In the second paper, researchers at the Singapore Institute of Technology added increasing amounts of the microalgae Nanochloropsis into a plant-based fish cake and how it affected its physical properties and in vitro digestion profiles. More specifically, they compared a surimi fish-based fish cake to a pea protein-based fish cake, then evaluated the varying inclusions of Nanochloropsis from 10, 20, and 30% replacement of the pea protein. The results showed that inclusion of microalgae created a product that more closely matched the texture and protein digestibility of animal-based surimi versus just pea protein alone. This was a comprehensive evaluation of end product functionality combined with nutritional composition and digestibility evaluation. To me, this really highlights the importance of hybrid products and full end product characterization of any new product. The last thing I want to talk about is the precision fermentation dairy sector, which has been very busy over the last 4 months. A few of the highlights include 6 patents from precision fermentation companies, including BioMilk, Change Food, Zhangjiang University, New Culture, Perfect Day, and Stand Innovation. There were also 4 patents for plant molecular farming for dairy proteins. Elsewhere, the precision fermentation dairy startup, the Vici, was announced from the joint venture between 2 multinational giants, DSM Firmenich and Fonterra. Next, highlighting the importance of academic alt protein research, a master's thesis on precision fermentation casein was published that is connected to the new startup Daisy Lab in New Zealand. There was also 1 self-affirmed GRAS announcement from Imagine Dairy. And finally, in the literature, there was 1 dairy review paper for precision fermentation and a casein micelle analysis on protein phosphorylation. I also just wanted to take a moment to remind folks that dairy proteins are diverse. We often talk about just casein and whey, but these are actually categories of milk fractions that contain many different proteins. In whey proteins, we have alpha-lactoalbumin, beta-lactoglobulin, lactoferrin, and lysozyme as predominant proteins. And in the casein fraction, there are beta-casein, alpha-casein, alpha-1 casein, alpha-2 casein, as well as kappa-casein. So let's just stick with caseins, which enable cheese. In milk, caseins are associated into large globular aggregates called casein micelles. Their main biological function is to transport and deliver proteins, calcium, and phosphate to young mammals. And in order to make cheese, these micelles have to stick to each other to form curds, and through acid coagulation and enzyme rennet cleavage of the kappa casein to create the full-on curd. A study from Wageningen University assessed the importance of casein phosphorylation and casein micelle formation. And this has been a really big question surrounding precision fermentation derived caseins. Their research utilized bovine casein, which they dephosphorylated with alkaline phosphatase. They then assessed the micelle formation from dephosphorylated and native casein proteins. They found that the dephosphorylated caseins stabilized the calcium phosphate nanoclusters, but it impaired the cheese curd formation upon renneting. So their research finding states that phosphorylation is crucial to micelle formation and sufficient curd formation during renneting. However, in a similar approach, but counter to this paper, the precision fermentation cheese company New Culture has had a number of patent applications and product demonstrations that show the possibilities of dephosphorylated precision casein with proper end product formulation assessment. Their patents demonstrate production of alpha casein or kappa casein in either the full length or the truncated versions produced from bacterial strains without post-translational modification. Their recent patents assess several formulation recipes with either precision alpha casein as well as varying mixtures of alpha and kappa casein. They then compared this to casein sourced from animal-based dairy and also assessed formulation with dephosphorylated animal-based caseins. What's really important is that these patents highlight the need to think outside of the box in terms of end product formulation. The goal should not be to mimic current cheese production technology and proteins 100%, but rather to create formulations that yield the end product characteristics with the protein and the strains that we have at hand. Next, I'll turn it over to Elliot for the latest developments in cultivated meat.
Right, thank you for those updates, Lucas. So June was a big month in the United States, with the USDA simultaneously providing grants of inspection to Upside Foods and Good Meat, meaning that each company now had the full green light to sell cultivated meat in the United States. Just a few weeks later, both companies debuted their cultivated chicken products at world-class restaurants in San Francisco and Washington, D.C., respectively. While the products will be available in very limited quantities for the foreseeable future, the approval will allow each company to receive valuable consumer feedback and has also generated a lot of global excitement over the arrival of an improved future food system. Not long after the US approvals, the company Aleph Farms, based in Israel, announced that it had submitted safety information to regulators in Switzerland and the United Kingdom. Both countries sit outside the European Union's lengthy novel foods regulatory framework, making them attractive entry points to reach European consumers. Aleph Farms currently has its cultivated steak product under regulatory review in Singapore, Israel, Switzerland, and the United Kingdom. At GFI, we received many questions about the cells being used in the cultivated meat industry. How are they procured? What animals are they derived from? What characteristics do they have? Is genetic engineering being used? And what would make a cell line certified as kosher or halal? Late last year, to answer all of these questions, GFI scientists, in collaboration with the Chris Meat Center in Singapore, conducted a survey that asked dozens of questions about cell lines being used for cultivated meat production. We received responses from over 40 companies, which have been compiled in a new report that was released in June. The report is an invaluable resource for anyone interested in providing high-value cell lines for the cultivated meat industry, an area that is still somewhat neglected. But more cell lines are becoming available for researchers every month, so please be sure to check out our up-to-date database on our website for the latest available information on cell lines for researchers. It's been well known for decades that glutamine metabolism into ammonia leads to a decrease in cell viability at certain concentrations, typically between 3 and 5 millimolar for animal cells. This buildup of ammonia poses a challenge for achieving scaled production of high-density cell cultures, and is one of the reasons why perfusion systems have been developed and implemented. To overcome this, scientists at the company Mosa Meat came up with a solution, avoiding glutamine altogether. They showed that bovine adipogenic cells can proliferate and differentiate in the absence of glutamine, instead relying on TCA cycle metabolic intermediates such as pyruvate and alpha-ketoglutarate. Doing so prevents the buildup of ammonia to toxic concentrations, as shown in the two figures on this slide representing both proliferation and differentiating cells. This simple solution could open the door to more intensive processing, ultimately leading to larger scale and lower cost cultivated meat production. Each time a technoeconomic analysis of cultivated meat is published, we learn a little bit more about what influences the cost of production. In this white paper published by scientists at ARC Biotech, they provide various scenarios that show cost parity is possible for cultivated meat, but it could require bioreactors that are much larger than what has ever been used to grow animal cells. The study suggests that current technology results in cultivated meat costs that would be around $30 per pound. But this could drop to around $2 per pound if cells are grown in bioreactors up to 1 million liters in volume, if media costs are reduced to as low as 50 or 25 cents per liter, and if differentiation results in a substantial addition of biomass to the end product. Additionally, hybrid products could ease the path to cost reduction by requiring less dramatic increases in bioreactor size or reductions in media costs. Like other analyses before it, this TEA adds new insight into the cost drivers of cultivated meat production and provides a roadmap for companies and researchers alike to hone in on what matters most for cost reduction. Technoeconomic studies like the one mentioned previously demonstrate the importance of reducing cell culture media costs. But it's not simply about the cost of the ingredients. Equally important is how efficiently the media is used. A longer-term challenge, therefore, for the cultivated meat industry will be formulating media that results in low feed conversion ratios by tailoring the ingredient composition to the metabolic needs of each cell line. And this can be aided by the creation of genome-scale metabolic models. In this review article published by GFI research fellow Sandra Romero, it's discussed the types of data and different techniques that can be used to leverage systems biology and metabolic modeling for cultivated meat. The paper describes what information currently exists and what will need to be created to get to a future where turnkey media development solutions are widely available for the cultivated meat industry. I'll now turn it over to Claire for updates on the alternative seafood.
Thanks, Elliot. I'll just be giving a couple quick updates on some new papers in cultivated seafood. So first, in June, we were excited to see the publication of a paper describing a new mussel cell line from Rohu carp by GFI grantee Dr. Mukunda Goswami. The cell line was derived using explant cultures, and the research team characterized its needs in terms of temperature, FBS, and recombinant growth factor needs. They also demonstrated that the cells could adhere to and proliferate on mushroom-based scaffolds. Development of appropriate cell lines is still a major bottleneck in cultivated meat, and this is especially true in cultivated seafood research. So we're happy to see this latest publication beginning to address this challenge. Also in June, we saw the publication of another paper led by a GFI grantee, Dr. Reza Ovesipor, describing his team's efforts to optimize fish culture media using AI and machine learning. The study focused on optimizing the concentrations of 7 media components with the end goal of maximizing the growth rate of the cells while minimizing the cost of the media and the global warming potential associated with ingredient production. While it is likely that the optimal media formulation will differ substantially between species and between cell types, both the media formulations themselves that were developed here and the methods used to arrive at those formulations may provide a framework for optimization efforts focused on other aquatic cell lines in the future. Finally, I wanted to quickly highlight the fact that a couple of studies we've previously mentioned before on these updates, when they were initially released as preprints, have now made it through the peer review process and have been officially published. So our team was very excited to see the final versions of both of these studies. And I'll now turn it over to Simone for some updates on ecosystem level analyses.
Thanks so much, Claire. I'll close out our snapshot by reviewing 2 studies which highlight the environmental benefits of alternative proteins. Life cycle assessments repeatedly show that eating less meat, particularly beef, results in significantly lower environmental impacts, but most LCAs compare individual products rather than the total impact of the collection of foods that make up a specific diet. This new study from the University of Oxford, published in Nature Food, quantifies the environmental impacts of dietary groups using one of the largest data sets on actual dietary choices across the UK. As highlighted by our GFI Europe colleagues, the study found that the diets of high meat eaters, consuming more than 100 grams of meat per day, result in almost twice the carbon emissions per day compared to those who eat small amounts of meat, and 80% more than diets without animal foods at all. To put this into perspective, if all high meat eaters in the UK reduced their meat consumption, it would have the same environmental impact as taking 8 million cars off the road. Additionally, low meat or no animal food diets use significantly less land and have a lower impact on biodiversity. This study further tested their conclusions by incorporating the range of environmental impact estimates of each food type using 570 life cycle assessments. As you can see in the center figure, even with uncertainty factored in, significant differences in greenhouse gas emissions remain between high meat and low meat or no animal food diets. This study demonstrates an important role for alt proteins in the transition away from high conventional meat diets by providing equally delicious, affordable, and accessible options. Finally, a novel study conducted by Asia Research and Engagement explored the role of alt proteins in achieving the greenhouse gas emission reductions goals of the top 10 major Asian markets out to 2060. The study estimated the amount of business as usual emissions that would need to be offset to reach a climate safe scenario, then explored the contribution of several emissions reduction strategies. As is shown here for China, the business as usual scenario results in 17.9 gigatons of carbon dioxide emissions in excess of the climate safe scenario. In addition to eliminating deforestation, transition to renewable energy, and reducing food waste, the study found that industrial animal protein will need to peak by 2030, and alternative proteins would need to reach a market share of 50% for China to reach a climate safe scenario. For other countries, the required alt protein market share ranged from 30 to 90%. To achieve this level of market share by 2060, significant investment and technological advancement is required to reach taste, price, and nutritional parity and appeal to the Asian consumer base. And with that, I'll pass it back to you to close us out, Liz.
Great. Thank you so much, Simone. That wraps our State of the Science snapshot covering May through August of 2023. Again, these highlights represent just a curated collection of the most noteworthy developments in the field from our subject matter experts, not a comprehensive list of everything that's happening. So to stay up to date at a more detailed level throughout the whole year, get updates about all of our resources and publications in real time by following us on social media and enrolling in our newsletters. If you'd like a deeper dive on the science at any time, check out our very detailed explainers, which link to tons of additional research papers and resources in our alt protein literature library. These snapshots and all of the insights and research and resources that GFI offers are made possible by our family of donors. If you're interested in supporting more events like this and all of GFI's work to advance the alt protein ecosystem, please contact philanthropy@gfi.org or visit gfi.org/donate. Thank you for tuning in.